Good evening. Welcome back. Tonight, we're going deep. Not metaphorically, literally. 600 meters beneath the surface of the open Pacific, into one of the most inhospitable environments on the planet, to find a creature that has survived there quietly for over 100 million years. Take a slow breath. Let your body settle. We're going somewhere very dark. At 600 meters, the ocean changes character entirely. The pressure here is over 60 atmospheres, 60 times the weight of the atmosphere pressing against you right now. The temperature holds steady between 2 and 4 degrees Celsius, year-round, decade after decade, century after century. No seasons, no variation. The water is cold, heavy, and absolutely still. But the defining feature of this depth isn't the pressure or the cold, it's the chemistry. This stratum is called the oxygen minimum zone. Here, dissolved oxygen drops to below 0.1 milliliters per liter of seawater, less than 1% of what's available at the surface. For almost any advanced marine animal, this isn't just an inhospitable environment, it's a wall. The metabolic machinery of active life simply cannot function here. It is, in the most literal sense, a desert, vast, dark, and suffocating. And yet, floating motionless within this chemical void, completely at home, is Vampyroteuthis infernalis, the vampire squid. The name is a product of human dramatics, a response to its dark, velvety webbing and the deep red of its eyes. In reality, it is neither squid nor octopus, but the sole surviving member of its own ancient phylogenetic order, the Vampyromorphidae. It doesn't hunt. It doesn't chase. It doesn't compete. It is, instead, a masterclass in what happens when a lineage commits fully to the physics of restraint. Then, in the absolute dark, something shifts. The void resolves into a pattern of light, not scattered, not chaotic, but disciplined. Dozens of blue-green points pulse across the creature's body in independent, controlled sequences, transforming the darkness into a controlled matrix of living light. The vampire squid's ability to produce and manipulate light is unlike anything else in the cephalopod world. Most bioluminescent animals flash uniformly, their light triggered by simple systemic pulses. Vampyroteuthis infernalis operates more like a precision lighting console. Its photophores, the light-producing organs embedded across its skin, can be activated and extinguished completely independently, in different sectors of the body, at different intensities, simultaneously. No other cephalopod on the planet does this. The photophores are concentrated at the tips of its arms, the bases of its fins, and distributed strategically across its mantle. Each one is a small feat of biological optics. At the center sits a cluster of photogenic cells. Behind them, a layer of crystalline platelets arranged as a parabolic mirror directs emitted photons outward with maximum efficiency. Overlying everything is a cellular lens, capable of physical dilation and contraction, that can shift the emitted light from a wide, diffuse glow to a sharp, intense point. By gradually dimming photophores on its fins while maintaining output at its arm tips, The squid can appear to shrink and recede from an observer while remaining completely stationary. To a predator tracking its silhouette, the target seems to accelerate into the distance and vanish. This isn't passive camouflage. It's active spatial misdirection, rewriting the geometry of the predator's visual field in three-dimensional dark. The lens itself is built from concentric layers of high-density proteins called crystallins, arranged in a precise concentration gradient, highest at the center, tapering toward the edges. This is a graded index lens design, the same principle used in high-end scientific optics, which corrects for spherical aberration and focuses emitted photons into a precisely aligned beam. By adjusting fluid pressure in the surrounding tissue, the squid can alter the lens curvature, shifting the output from a diffuse ambient glow to a high-contrast point of brilliance without moving a muscle or spending additional metabolic energy. The chemistry behind the light is equally refined. Inside the photogenic cells, a substrate molecule called luciferin rests dormant alongside its catalyst enzyme, luciferase. When a neurological pulse triggers a photophore, a small, precisely regulated dose of intracellular oxygen enters. The luciferase oxidizes the luciferin, forming a briefly excited molecular intermediate. As that intermediate drops back to its ground state, it releases its excess energy not as heat, but as a single photon, peaking at exactly 470 nanometers. Blue-green. The wavelength that travels furthest through seawater, experiencing the lowest possible rate of scattering and absorption. The light is tuned to its medium with the precision of a musical instrument to its concert hall. Every adaptation in the vampire squid's anatomy is an answer to the same constraint. Oxygen is scarce, and every expenditure must be justified. The animal has solved the energy problem by largely eliminating the need for active effort. Its body tissue has been systematically replaced with a low-density gelatinous matrix rich in ammonium ions, giving it near-perfect neutral buoyancy. It doesn't swim to hold its position. It floats effortlessly within the fluid envelope of the deep Pacific, a weightless presence that expends almost nothing just to exist. This gelatinous architecture is non-contractile, meaning its density remains constant regardless of changes in external pressure. Instead of continuous muscular correction to maintain position, the animal relies entirely on passive density matching. This drops its resting metabolic rate to the lowest recorded among deep-sea cephalopods. The energy it doesn't spend on staying afloat goes toward running its nervous system and keeping its photophores available on demand. Its respiratory mechanics are correspondingly precise. The vampire squid has large, well-developed gills relative to its body mass. Its blood carries a specialized hemocyanin, a copper-based oxygen transport protein with an extraordinarily high binding affinity. Even in water holding only trace dissolved gas, this hemocyanin strips oxygen from the medium with near-total efficiency, channeling it directly to the organs that need it most. Its skin handles the remaining problem: visibility. The deep, velvety pigmentation, ranging from jet black to a dark chocolate brown, comes from an exceptionally dense concentration of chromatophore cells packed with mature melanin granules. Unlike surface cephalopods, which continuously expand and contract chromatophores for dynamic camouflage, The vampire squid's skin cells have lost their muscular connections entirely. They rest in a permanent state of maximum expansion, requiring zero ongoing neurological energy to maintain. The result? The skin absorbs over 99% of any light that strikes it. When a predator sweeps bioluminescent searchlights across the zone, the vampire squid doesn't reflect the photons back. It drinks the light, and the silhouette disappears. The vampire squid's feeding strategy is the logical conclusion of every adaptation described so far. It doesn't hunt. It doesn't chase. It is the only known cephalopod that doesn't prey on living animals at all. Instead, it feeds entirely on marine snow, the slow, continuous downfall of organic debris from the ocean above. From the sunlit surface layers, a silent avalanche drifts downward through the water column at all times. Microscopic fragments of dead plankton shed mucus, fecal pellets, and trace biochemical particles that bind together into delicate organic flakes. As this material descends through cold, dense water, its rate of fall slows. In the oxygen minimum zone, it drifts with exceptional patience. To harvest it, the vampire squid extends two retractable filaments, thin, thread-like organs stored in dedicated pockets within its webbing. Extended, these filaments can reach up to 8 times the total body length of the animal. They trail through the water column covered in microscopic adhesive cells coated with glycoproteins that bond on contact with the porous matrix of marine snow. The filament itself remains completely limp during deployment, creating no turbulent fluid signature, no detectable wake. It is, in effect, invisible. When a filament is loaded with organic material, a slow, low-energy contraction wave draws it back through the webbing. The arms of the squid are lined with soft, flexible projections called cirri that sweep the collected material off the filament and channel it toward the beak. The beak itself, unlike the heavy, calcified beak of surface cephalopods built to tear live prey, is thin, lightly mineralized and flexible. It functions as a gentle funnel, not a weapon. Every gram of heavy calcified tissue that wasn't built represents metabolic capital that didn't need to be spent. This feeding strategy connects the vampire squid to the planetary scale. Every photon captured by a diatom in the surface waters of the North Pacific eventually contributes, months later, to the energy budget of Vampyroteuthis Infernalis. The carbon fixed in warm, sunlit surface waters drifts downward through the water column, cooling and compressing until it arrives in the oxygen minimum layer as organic snow. The vampire squid sits at the base of this slow conveyor belt, a patient, unhurried steward of the ocean's recycled energy. Without the need to hunt, the vampire squid's nervous system has been reorganized around a different set of priorities. Surface predators require brains built for speed, fast visual processing, rapid trajectory calculations, explosive muscular coordination. This costs an enormous proportion of daily caloric intake. The vampire squid's central nervous system is streamlined for something else entirely: long-duration, low-frequency monitoring. It processes information from its trailing filaments, integrates signals across its Photophore network, and reads the slow-motion dynamics of its environment with exceptional patience. Its eyes are the most striking expression of this design. Vampyroteuthis infernalis has the largest eye-to-body ratio of any animal on Earth. In mature individuals, the eyes reach up to 2.5 centimeters across, enormous relative to the animal's body mass, crystalline blue or deep velvet black, depending on how they catch the faint residual light. The retinas are dominated entirely by rod cells, arranged in an exceptionally dense, uniform matrix. No cone cells, no color differentiation is needed in a world with no color. Every rod is tuned to detect contrast changes within the narrow blue-green band. The lens is a large spherical crystal with a short focal length, concentrating every passing photon onto the retinal surface with maximum efficiency. A single photophore flashing hundreds of meters away is enough to register its precise coordinates. The squid doesn't need to turn its head or shift position. The information arrives passively at the speed of light. The eyes are oriented fixed outward and slightly upward, scanning the upper boundary of the animal's environment continuously. This serves two purposes: monitoring the density of descending marine snow to choose the optimal depth layer, and reading the silhouettes of potential predators passing through the slightly lighter water above. When a large animal moves across the upper horizon, its body briefly blocks the faint ambient downwelling light, casting a shadow across the squid's retina. The detection requires no movement, no energy. The information is simply received. When a threat is detected, the vampire squid doesn't flee. Fleeing would require muscular contractions that would rapidly drain its oxygen reserves and leave a trailing chemical signature of metabolic waste in the water, a beacon in the dark for anything with a sensitive chemoreceptor. Instead, it executes a behavior called the pineapple posture. It slowly draws its 8 webbed arms backward over its mantle, reversing its shape entirely. The dark, velvety interior of the webbing folds outward, covering the head and body. The tips of the arms, armed with soft white cirri and bright terminal photophores, point outward toward the threat. In this configuration, the squid transforms from a soft-bodied cephalopod into something that resembles a spiny, unappealing form. The white cirri look like sharp spines under faint light. Simultaneously, the photophores at the inverted arm tips activate, bright, erratic flashes drawing the predator's attention away from the vital organs. If the predator moves closer, the squid dims the arm tip photophores slowly, gradually. In the deep ocean, a light source that reduces in intensity reads to marine visual systems as an object moving rapidly away into the distance. The predator follows the false trajectory of the fading light, swimming past the stationary squid in pursuit of a ghost. Once the threat clears, the vampire squid slowly unfolds its arms, returns to its neutral hover, and resumes its routine, energetic budget entirely intact. If a predator breaks through the optical illusion and makes direct contact, the squid has one final defense. It releases a cloud of bioluminescent mucus from the tips of its arms. This is not ink. Black ink is useless in permanent darkness. Instead, the mucus is packed with concentrated luminescent particles that react instantly with seawater, erupting into a brilliant, swirling fog of blue-green light. The cloud hangs suspended in the water column for up to 10 minutes, blinding the predator's dark-adapted eyes with an overwhelming wash of photon emission. The mucus matrix is rich in dense mucopolysaccharides that prevent the cloud from dispersing quickly, keeping it concentrated and coherent rather than diffusing into a thin haze. Within the floating mucus, the luciferin-luciferase reaction sustains itself through a slow-release mechanism, maintaining the glow for the full duration. The squid, using its neutral buoyancy, slides silently into the surrounding dark, while the predator bites at empty, glowing fog. This response is metabolically expensive. It costs significant protein and luciferin compounds to produce, which is why the animal reserves it strictly for direct contact scenarios. It is a precisely calibrated emergency measure. Use only when all other options have failed. The vampire squid is not simply well adapted to the oxygen minimum zone. It is, in a meaningful sense, a product of it, forged by one of the most catastrophic periods in the history of the ocean. Approximately 94 million years ago, during the late Cretaceous, the Earth experienced a series of events called oceanic anoxic events. Massive volcanic activity injected carbon dioxide into the atmosphere, triggering warming that disrupted marine circulation. The deep ocean currents that normally carried oxygen-rich polar water toward the equator slowed to near halt. The middle layers of the global ocean became vast, stagnant basins of oxygen-depleted water. For the dominant high-metabolism animals of the Mesozoic seas, ichthyosaurs, ammonites, ancestral sharks, this was catastrophic. Their aerobic metabolisms couldn't function in the depleted middle layers. Ecological collapse followed across the pelagic zones. The ancestors of the vampire squid moved in the opposite direction. While other cephalopods struggled against the expanding anoxic layers, the early vampyromorphids descended into them, systematically colonizing the expanding oxygen minimum zone. They developed their gelatinous, low-density tissues. They tuned their hemocyanin to bind trace oxygen with unparalleled affinity. They converted a lethal chemical barrier into a predator-free sanctuary. When the Cretaceous-Paleogene extinction event struck 66 million years ago and decimated surface ecosystems, the vampire squid's ancestors were undisturbed. Deep within the stable boundary layers of the deep ocean, the catastrophe registered as nothing more than a gradual shift in the composition of the descending marine snow. The organism simply hovered, maintaining its metabolic equilibrium, while entire dynasties of surface life were erased from the evolutionary record. This is why Vampyroteuthis infernalis behaves as it does. Every aspect of its anatomy, the bioluminescent console, the gelatinous buoyancy, the passive feeding filaments, the graded index lenses, the pineapple posture, is not a response to current conditions. It is the accumulated record of 100 million years of quiet, structural refinement in one of the most stable environments on Earth. The oxygen minimum zone is not, by any measure, a marginal habitat. It stretches across millions of square kilometers beneath every major ocean basin. It has remained chemically consistent for millions of years, insulated from the volatile surface world above by hundreds of meters of water. While the atmosphere experiences storms, seasons, and climatic upheaval, this stratum simply holds, cold, dark, pressurized, and constant. The vampire squid has aligned itself with this constancy completely. It doesn't fight the darkness. It doesn't resist the pressure. It doesn't struggle against the scarcity of oxygen. It has organized its entire physiology around matching the conditions of its environment rather than overcoming them. Every line of tissue, every optical lens, every chemical bond in its bioluminescent pathway has been refined toward a single outcome: do as much as possible with as little as possible, and remain indifferent to anything that can't be used. As the night deepens, the photophores dim. Not all at once. They fade in a controlled, independent sequence, sector by sector, until the last points of blue-green light extinguish and the velvety silhouette dissolves completely back into the surrounding dark. The creature returns to its baseline state, hovering, still, invisible. The water above is cold and heavy. The marine snow falls with no urgency. Nothing about this moment is different from any moment in the last million years. Down here, past the reach of light and wind and season, the world holds its deepest, most permanent equilibrium. Let that image settle. Your breathing has slowed to something close to that rhythm. The analytical loops of the day are losing definition. There's nothing left to calculate tonight, no problem that requires solving before morning. The abyss is quiet. The squid floats in the dark. Good night.